Now we're going to continue talking about recursive algorithms. So an algorithm is a set of steps for solving some problem. A recursive algorithm is an algorithm which solves the problem by reducing it to one or more of the same type of problem, but for a smaller input value. So basically, I want to solve a problem. I split it up into sub problems, each of which has already been solved. Okay, so think about solving a problem as defining a solution, right? So our function is we take an input, and the solution to the problem is the output of our function. And so this, we think about it that way. A recursive algorithm is a recursive function where I have one or more base cases, but then the solution to my problem, which is the output of the function, is somehow obtained by previous smaller values of the function. Right? So there's not a lot to say here, in my opinion, because it's on the verge of not being a math course anymore. It's on the verge of being highly specific to computer science. So I think there is a lot of stuff of interest in both sections 5.4 and 5.5, but as far as we are concerned, there's not a lot for us to do. I highly recommend reading those sections of the book, as I think they might be helpful for you just in your major and elsewhere. But as far as we are concerned, we're not going to get too in-depth for section 5.4. We're going to look at some examples of recursive algorithms. We'll just look at two quick examples, and then that'll be it. So when we think of an algorithm, I said, kind of you take in an input and you output the solution. So our algorithms have to be slightly more than just a function. So one problem that we might want to do is take an input array of numbers and sort them into ascending order. Okay. So if you think about a function, my function is the set of all possible input arrays. And when I say array, I mean just a list of numbers. My domain for my sorting function is the set of all possible input arrays, and my outputs are just the sorted arrays. So that defines the function. Input is some array, the output is the same array but sorted in ascending order. That's the function. When we talk about an algorithm, you actually have to talk about what is the correct syntax for how to tell a computer how to do the steps that I'm talking about. You have to tell, when the algorithm involves, how are you actually going to tell the computer to do the sorting? And so there's a little more there, in fact, kind of a lot more there to the algorithm than just the description of what it does, which is what the function is. So we've already talked about like the factorial. So I'm gonna say definition. I'm gonna say factorial. I'm gonna put n. I'm gonna put a colon. I'm gonna say if n equals 1. I'm gonna say return 1. And I think in order to be consistent here, no, this is right. I'm doing factorial is not Fibonacci. If n is greater than 1, return, I'm going to say n times factorial n minus 1. So here, def means I'm defining a function. Factorial is the name of the function. This n in parentheses here tells me what the inputs are, what the name of my input is here. And then I have some conditional statements. If n is 1, then the function is defined this way. If n is greater than 1, it's defined this way. And here is the recursive part of the algorithm. This is because my function is calling a different value of itself. Okay. So this is a recursive algorithm for the factorial function. You can put this so appropriate, use the appropriate syntax, and you can actually get a computer to evaluate the factorial function correctly for positive integers. Okay. So that's not a very interesting example. I want to talk about a more interesting example, and I've mentioned it before in class, so we're going to go a little bit more in depth now with the merge sort algorithm. Okay. So The input is an array. When I say an array, I mean just a list of numbers. Okay. So the numbers are in some order, but not necessarily ascending order. And the output is ascending reordering of the input. So I'm going to put in some input array, and the output is going to be the same thing, but in ascending order. Okay. So so here we're going to talk about comparisons. Comparisons are going to be my unit of measurement of time. Okay. The fewer comparisons I can get away with, the better the algorithm is, the faster it is. Right? So we talked about this before. If I have an input array of size n, then we could just look at all the pairs. So just look at pairs and then switch them or don't switch them depending on if the one on the left is smaller than the one on the right. Okay, so they're arranged from left to right here. And I can swap or not after comparing all the pairs. If I compare all the pairs, then I end up with n minus 1 over 2 comparisons. And this is, I'm going to say, big O of n squared. It's all crushed together there. Difficult to read. This big O of n squared. Means this takes, if I'm going to do it that way, where I make all the comparisons, then I have to do on the order of n squared comparisons. The question is, can we do better? Okay. So the merge sort algorithm is a pretty interesting result. What I'm going to do is first say assume that we already have defined this merge function. So I'm going to have a merge sort function, which sorts the algorithm. And I'm going to have that sorts the array. And I'm going to have a merge function, which merges to already sorted arrays. Okay? So this merge function is a function in and of itself, and I'm going to use that inside the merge sort function later. But the merge function is going to take as its inputs two sorted arrays. Okay? So the inputs to the merge function need to be sorted already. I mean, the function will work even if they're not, but you don't get the right kind of output if you don't have the right kind of input. What I'm going to do is assume I have two sorted arrays, right? So I have B1, B2, B3, up to BP, and then C1, C2, C3, up to CQ. P and Q could be different. And I'm assuming these are my input arrays, and I'm assuming they're already sorted. So B1 is less than or equal to B2 is less than or equal to B3, and C1 is less than or equal to C2 is less than or equal to C3. I don't know anything about how the B's relate to the C's, but I know that the B's are already in ascending order and the C's are already in ascending order. So what I'm going to do is I'm going to allocate a bunch of memory, so P plus Q slots here, some array of size P plus Q, and I'm going to initialize two counters. Okay, so one counter for the B array and one counter for the C array. And what I'm going to do is start at the first numbers in each array, and I look at B1 and C1. If B1 is less than C1, then I put B1 here. So let's go ahead and assume that B1 is less than C1 for the sake of concreteness, and say, okay, if B1 is less than C1, I'm going to put this here. And then I'm going to increment my counter on that B array. Now I'm going to compare B2 and C1. So maybe B2 is still less than C1, so I'm going to put B2 here. I'm going to increment that. Okay. And now compare B3 and C1. Now let's say that C1 is less than B3, so that's what goes in here. And then I move on. And now I compare B3 and C2. Maybe C2 is less than B3, and I put that there, and then I increment again. And in doing that, I make, at most, P plus Q comparisons. And I think maybe even P plus Q minus 1 comparisons. And I'm merging these, and what I end up with is kind of the B's and C's also in ascending order. So when I get done with this is going to be these two arrays kind of ascended as well. So this is what I end up with here is going to be sorted. And the purpose of this is if I feed in two arrays that are already sorted, I can take advantage of the fact that they're already sorted. Because if I didn't know that these are sorted, I'd have to compare all of the B's to all of the C's, and I end up with P times Q comparisons, which is a lot more than P plus Q. Okay? But if I know that my input arrays are already sorted, I can take advantage of that, okay? And cut down the number of comparisons I have to make from p times q to p plus q. So you can actually go, based on what I've said, you can probably go figure out how to write this program in your favorite language. Write the merge function. Now the merge sort algorithm is going to take an array and it's going to output the same array but sorted, and it's going to use the merge function. So I have two functions here, merge and merge sort. Merge is defined, and then we're going to use the merge function inside the merge sort. So what we're going to do is say, well, if n equals 1, the array is already sorted. It only has one number in it. Okay, so this is kind of the silly case. If n equals 1, and if n is not equal to 1, if n is greater than 1, so I'm going to say let r 1 up to rp be a1 up to a n over 2, the first half of the input array. Okay. And then I'm going to say s1 up to sq equals the second half. So take the an array, I split it in half, and this is a new array that I'm calling r1 up to rp. Here I get s1 up to sq. Okay. Now what I do is I'm going to say take the r's and sort those. Okay, so I'm going to say merge sort r1 up to rp. So take the big array, split it in half, take the first half, put it in the merge sort function. So here this is the recursive part of the function, is I'm defining the output for this input array in terms of the output for a sub-array. Right, so my algorithm solves the problem by solving a smaller problem of the same type. Sort the whole array by sorting the first half, and I'm going to sort the second half. Okay. And then, so I have the first half, and I sort it. And I have the second half, and I sort it. And then I merge those together using the merge function that we defined in the previous page. So, maybe it's not clear why this actually does better. So why does this actually do better than the n squared algorithm that compares all of the pairs, right? So here we had this n squared algorithm. Here we have some other algorithm. How do we know it's better? Okay. So this is the merge sort. So here I write return. Here I can say return. This is the merge sort function. And that's more or less it. I mean, you have to make the syntax correct, but you have basically everything you need here in order to go write this function yourself in your favorite language. So why is this better? Well, let's say Tn is worst case scenario for input of size n. Okay. So worst case scenario, what I mean is, how many comparisons does it involve? Okay. Because that's how we're measuring the unit of time. Fewer comparisons means faster algorithm. So Tn, worst case scenario for an input of size n. So it means if I put in an array of size n, what is the greatest number of comparisons that we have to make using the merge sort algorithm? Okay. And then I misspoke. Comparisons count as one time unit, and the merging, the comparisons involved in merging also count as a time unit. I guess I didn't misspeak. I'm good. So remember the merging. Merging here takes p plus q time. Okay. So here I take an array of size n. On the Tn, how long is this going to take? How many comparisons will it take? So what I'm going to do is I'm going to split n over 2, and then merge. Okay? So I have this, the first half, how long is it going to take to sort that? Well, it's going to take n over 2. Right, so I take the first array of size n, split it in half. What's the worst case scenario for sorting the first half? Well, the first half has length n over 2, so that's the worst case scenario for sorting the first half by definition. What's the worst case scenario of sorting the second half? It's also t n over 2. So sort that one and sort this one, add them together, right? This many comparisons to sort the first half, plus this many for the second half, plus how many happen outside the algorithm, right? Outside the sorting algorithm. How many happen in the merge, right? So here I'm going to put n. Right? So here, I'm doing the merge is p plus q comparisons. And I'm going to have p is n over 2 and q is also n over 2, so I get p over 2, or p plus q is n over 2 plus n over 2, which is n. So here, if you want to be really careful, you have to worry about other operations besides comparisons. And so you might end up with a constant here, but that constant doesn't change the asymptotic nature of what we have. It doesn't really change the correct upper estimate in terms of big O notation, if you know what that is. And so here, so we end up with Tn is less than or equal to 2, Tn minus 2 plus n. And now, if you solve this recursion, which means well, a couple of ways to do it. There's a master method, there's a substitution method to prove your result once you have it. Right? You can prove by strong induction that there exists a constant c such that t of n is less than or equal to c times n, capital N, times log n. So here, the kind of the worst case scenario in terms of number of comparisons is less than or equal to some multiple of n log n. Multiple, I think, I know 6 works. That was what was used proof that I completed. 6 is, maybe you can do better than 6, but definitely 6 will work. And so here we're comparing n squared to 6 times n log n. And if you look at large values of n, this is much, much smaller. This log n is much smaller than n. Okay. So this is, in my opinion, one of the fundamental examples of a recursive algorithm, and well, maybe not a complete, but a fairly complete discussion of how you would actually sit down and write this in your favorite language, and why you would care about it. Is because here I have in the amount of time this one takes is n squared, the amount of time that this one takes is n log n. And that's much better.